Hi, I'm Brendan.
I'm Ryan.
And we did our research on multimodal machine learning. What is multimodal machine learning? Well, a modality is a way we experience the world around us. For instance, visual or language or vocal signals. And multimodal machine learning develops models that combine information from different modalities. In multimodal machine learning, you use tools from many areas of computer science, such as natural language processing, computer vision, and of course, machine learning. So why should we care about multimodal machine learning? Well, it has numerous applications to important problems in machine learning. These include audio-visual speech recognition, which could be transcribing a video of a person speaking. Another application is multimedia content, processing multimedia content, so for instance, video analysis. There's also understanding human social interaction, and there is the application of media description. So for instance, providing captions for images for the visually impaired. And here is an example of an application of multimodal machine learning. This slide is from a study led by Professor Morency from CMU on multisense, which is a model that has the ability to detect human emotions using multiple modalities. In the study, patients were interviewed by fully automated digital interviewers, and multisense was able to detect levels of distress or other emotions from the patients, which helps with diagnosing post-traumatic stress disorder. And the model uses information from many modalities, including body language, speech, and facial patterns.
So, what are the challenges that are faced in multimodal machine learning? There are 5 different areas in multimodal machine learning research, as identified by Professor Morency and his graduate students here at CMU. These 5 areas are representation, translation, alignment, fusion, and coding. Representation deals with the challenges that involve encoding data from a modality in a way that can be interpreted by multiple different modalities. In translation, researchers are concerned with converting from one modality to another. In alignment, researchers try to take information or objects from different modalities that are known to be connected, or known to be connected, and try to draw connections between them. So, for example, in this study, researchers had movie clips and passages from their respective books, and they wanted to identify which part of the book each clip of the movie is from. In fusion, researchers use different data from different modalities and try to learn something important from combining all the different data from the multiple modalities. And in this case, the different modalities are different perception tools. And co-learning, in co-learning, the challenge is to use data from a modality with large data sets to aid with learning on data from smaller data sets. So I'll give more details on research that's being done in the area of translation. So in translation, you're given an object in modality A, such as text or images or video, and you want to generate an equivalent object in modality B. So some examples of this are text-to-speech, visual speech generation, speech synthesis, and visual scene description. Visual scene description is an area of multimodal research that's been very popular recently, and for the most part involves trying to caption images and videos in a way that increases computers' understanding of those images. And there are two types of translation, or two types of models used in translation. One of these areas is example-based. Example-based models use dictionaries to translate between the two modalities. So similar to how I might look up words in another language, in a foreign language dictionary. These models will do the same thing. However, since the dictionaries just contain like an entry for each possible object in the modality, these are very space efficient or space inefficient, and they're also finite. So no matter what, there will be a set of objects that you won't be able to translate properly. On the other hand, we have generative models where you have a unimodal source and you want to perform translation into multiple different modalities. And there are three types of these: grammar-based models, encoder-decoder models, and continuous generation models. So in grammar-based models, researchers will define a grammar for each output modality, and when they're given an input, they map that to a sentence in the grammar structure for that target modality. In this example, the grammar is defined to describe different poses and actions that the human body can take. And so the input is a video, and the task is to describe what actions the human in the video is performing, and uses well-defined grammar to do this. In encoder-decoder models, the main computation is neural net, and so the input is encoded into a vector which can be fed into the neural net, and then the output from the neural net is then decoded into the target modality. In this case, the input video is vectorized into data, and then they wanted to, the goal is to output a description of the video. And in this case, they use both convolutional and recurrent neural networks.
Okay. So fusion is one of the most studied areas of multimodal machine learning. Fusion creates models that combine information from different modalities in order to predict some sort of measure, which could be human emotion, say. And because fusion combines this information from many different channels, it allows for more robust predictions that might gain particular insight into one of the channels used. And two common approaches for fusion-based models are multiple kernel learning and neural networks. So multiple kernel learning uses kernel support vector machines to model each of the different modalities that are used. And the example is the work of McPhee and Lancret in multimodal similarity. So they worked on the problem of measuring the similarity between items that have multiple different ways that they could be measured. So for instance, with musicians, you can compare them with the rhythm of their music, or the lyrics in their songs, or their biographies, say. And what they did was they asked humans these queries, of whether musician I was more similar to musician J or musician K. And this was converted to this constraint of distance, where distance between I and J is less than the distance between I and K, as shown here. And this in turn was fed into the model. And you also see in this diagram that each of the three feature spaces represents a different modality, and each of those is encoded by a different kernel, hence the multiple kernel learning. And currently one of the most popular models for multimodal fusion is neural networks. The advantages of neural networks are that they can learn from very large data sets, and they can sometimes produce more complex prediction models. However, disadvantages are you need a large data set to use them. So if you don't have a very large data set, then you have to resort to something like multiple kernel learning. And neural networks also are harder to interpret, so they can give you a prediction model, but then it's harder to figure out what factors were important in that prediction. An example of neural networks for fusion is the work of Neverova et al. In gesture recognition. And you can just see here that the multiple modalities used in recognizing gestures of audio, visual, and depth.
So here at CMU, a lot of the research in multimodal machine learning is driven by the multi-conf lab. This lab is led by Dr. Luis Morenzi, who we mentioned earlier, I think. He's done a lot of his research in multimodal machine learning, as well as human communication dynamics and health behavior informatics at the multi-conf lab. And specifically, one of the areas of multimodal machine learning that they're researching currently is grounded language learning, which is attempting to have computers learn the meaning behind information from different modalities, whether it's text, image, or video. And that's it. Thank you.